batch processing and
stream processing.
Stream processing is.
Okay. Anybody else? What do you remember about Flink? Anybody else? Anybody else remember anything about Flink? Okay, so when we talk about the different component of the Flink program, so what are the three components of the program? So the first one was the data source. What is the second one and the third one? The main component of Flink program. So a Flink program will have a data source. What else it's gonna have? Sorry?
Isn't it transformations and data sync?
Perfect. So we have a data source where the data come from. We have transformation, and then we have data sync. Can you give us an example of the data source? Any example of a data source? Okay, so in terms of data source, the data can come from your database. That's one simple example. It can come from your database or from any other source. Okay. Okay, so today we're gonna talk about the time semantics supported by Flink. So we have processing time and event time in Apache Flink. So these time are different from, remember what we said yesterday, that every event will be given a watermark. So basically, we're going to record, the computer is going to record at what time an event happened. So understanding time semantics in Flink is very crucial. Why? It's crucial. Why? Because of the stream processing. Events are happening in real time. So in Flink, we have processing time and event time. Event time can also be called raw time. So processing time is basically the time that you have on your clock. Okay, which can be 12 o'clock or 12:31. You understand, something like that. Okay, but the event time is the time when the event actually occurred. So when the data was generated, what was the time at that time? Okay, and the current time would be the processing time. Okay, so in terms of processing time, the processing time will be the time when Flink process the event. What's the time on the clock of the machine, depending on what time is it on the machine. And then we will have some of the characteristic of this time is that it will be we're not going to have a problem. We have a low latency of how the data are moving, so we're not going to have any delay because we will have some delays because of the network. So think about it. If the network is not picking up the time properly, it's going to give you a wrong information. All right. So if the network is not picking up what's the current time when the event is happening due to maybe network problem, that is going to create a bit of inconsistency and a certain delay, which is created by the network. Okay. So when do we use the processing time? We use the processing time when we're dealing with things like application where speed really matters more than accuracy. Example, when we're dealing with real-time monitoring, like for cameras, or security, things like that. So the processing time is actually the time in the real world. It's basically the local time when the data node is processed. It is simple. It's used in simple processing. Okay. But the problem is uncertain results because it cannot be reproduced. It was the actual time when the data, the time in the real world when the data was processed. Okay. So the event time will just be the time when the data is generated. Timestamp carried in the record. This can be used in complex processing. For certain results, it can be reproduced again. So in the event time, you basically have the timestamp of the event. So this can be considered as accurate. It's used in most cases like, for example, you have a billing system where you need to record at what time something was, some event happened, so that you can maybe bill your client or something like that with the system. In terms of fraud detection, for example, in a building, it can see at what time a certain event happened. It was followed by something else. It basically record certain time when the data were generated. Okay. Okay. And then the next thing will be windows. What are windows in Flink? Yesterday we spoke about tumbling window and sliding window, where we gave you the example of an event happened in 5 seconds. So that 5 seconds is a window. I gave you the example of the OTP. When you have an OTP, when you generate an OTP, there's a certain window that can be maybe 5 minutes. So in 5 minutes, the OTP is not going to be valid anymore. So basically, in streaming system is a data processing engine designed to process infinite data sets. Infinite data sets refer to constantly growing data sets. So window is a method of splitting infinite data sets into kind of blocks for processing. So basically, we have certain blocks of data that will be processed in a certain window. So in 5 seconds, for example, we're only going to process a certain group of data, and then the next window will process another group of data. This will help so that we are dealing with all this amount of data. So windows are the heart of processing infinite streams. Windows splits the stream into buckets of finite size over which we can apply computation. Okay, so we can classify the windows into 2 types. So the first type will be the count window. The second type will be the time window. So the count window will be based on specifying numbers of data record. Okay, which does not depend on the time. We're not going to involve the time in it. And then when we talk about the time window, this is a time-driven window. When the time-driven window is generated based on time. So we're creating this window based on time. As I said, we have an event time session which has a window of a gap of maybe 5 minutes. All right. So that can be a session window, or we can have what we call a global window, as we spoke about it yesterday, where you have something that can happen. It starts, but it doesn't have an end. So the window can be as long as the system is working. Or you can have something like a sliding window or tumbling window. Okay. So according to the window implementation principle, time window can be classified into tumbling window, sliding window, and session window. That's what I just said now. So in terms of tumbling window, you need to understand that in the tumbling window, the data is sliced according to a fixed window length. The time is aligned, the window length is fixed, and the window do not overlap. So this is an example. We have input of this data here. So in the tumbling window, so the first window, we're going to process this data. And then the second one, so maybe we're going to have this one, this third one, we have that one. And the window do not overlap. Okay. So some application scenario we have in statistical collection, for example, aggregation calculation in each time period. For example, we assume that you want to count the values emitted by a sensor. A tumbling window of 1 minute collect the values of the last minute and emit the sum at the end of the minute. So this is the example here, and then the sum will be 27. This one. So at each window, it's going to take some of the data and whatever operation. In this case, we are getting the sum. So it's giving us this. That is a tumbling window. But the difference between a tumbling window and a sliding window is that first of all, they both fix size. So we already fixed the size. But in the sliding window, the data can overlap. But in the tumbling window, the data do not overlap. Okay, so this is an example here. Okay, so an example of a scenario can be to collect the statistics on failure rates of an interface over the past 5 minutes to just determine whether to report an alarm. Okay, so a sliding window of 1 minute that slides every half minute, count the values of last minute, emitting the count every half minute. So we have something like this. So every half minute, we have more data. Okay, you can see they overlap. So that's the difference with that. But the session window will just consist of series of events, and a timeout interval is a specified duration. Okay, so it is similar to a web application session. So basically, when you think about it, it's like when you're using an example I can give you here is you're using a system that allow you, when you look at many websites or many systems, if you don't interfere with the system for maybe 5 minutes, it's going to log you out. But the system is on as long as you're interfering with the system. So we have a window, which is a session window. So as long as you are using the system, it's on. But it has intervals. So it basically have gaps in between events. And the gap in between events, it means if you're not doing anything on the system anymore, for a certain period of time, it's logged you out. So those are session gaps. So that is a session window. Okay. So the way we're going to define it in when we coding, example of when we coding, for example, you want to deal with a time window, we're just going to say string.time window, and then we determine that's the time we want to use minutes. So this is a 1 minute. So if we have a slice time window of 1 minute, slice every 30 seconds, we can define it as this one. It's time window with 1 minute and 30 seconds. So it lasts every 30 seconds. Okay. Okay, so Flink watermark. So what is a Flink watermark? So basically, in Flink, the watermark will be a very critical mechanism that can help us handle event time processing in all the streaming application in Flink. So basically, there's a process. There's a process from event generation to stream processing through the source, then the operation. Okay, so in most cases, data is sent to the operator based on time when the event is generated. However, out of order data may be generated, such as events received by Flink are not sorted strictly based on the event time due to network problems. So I think yesterday I spoke about this. When we're going to have an ideal situation where the way the data arrive, let's say you have certain data that need to arrive at a certain time because maybe an information in data 2 will need information in data 5 to operate. So the way you're receiving information from the source before transformation, when you're receiving the information, they come in this order. This is the ideal. So it's going to be based on how the information has to be. But sometimes because of network, there may be certain data that can be out of order, such as this. This is the actual situation. Okay, so this is an example. An app record all user clicks and send logs back. You know, when you're dealing with, let's say, for example, you're dealing with a certain system that you've created, and then your client tell you there was an issue. Some users were using the system, now it was crashing. And then when you ask at what time it happened, they tell you it happened at 12 o'clock. But when you're looking in your system to see the log that record all the errors and all the problems, you see that it's giving you a different time. So this is what we're talking about. So certain events may occur at a certain time, but the information in your log come in different times. So you can see the way the event was happening is not the right way. So different event was happening in different time, but it was not in the proper order in your system. So when you look back now in your logs, so if the network condition is poor, the logs are saved locally and sent back later. So this is a way when how Flink can do it. So it saves everything locally in the wrong order and then fix it and send it back. Okay. So an example, this is the example, I'm just gonna read it all. An app record all users click and sends logs back. If the network condition is poor, the logs are saved locally and sent back later. User A performs operation on the app at 11:02, and user B perform operation at 11:03. However, the network of user A is unstable and log back all is delayed. As a result, the server received the message from user B at 11:03 and then the message from user A at 11:02. So what example can I give you in this case? Okay, this is a perfect example. You trying to chat with someone, right? So you send them a message. It's 12 o'clock at your time, not even 12 o'clock. Let's say it's 11:02. Let's take this example here. 11:02. You send a message. But because your network is bad, the server has not recorded that message. So it's still loading. You're still sending the message. But the person take the phone at 11:03. They have a good internet. They already send you a message. And when they send you the message, you receive the message before your message can go. I don't know if you understand what I'm talking about. You receive their message before yours can go. Now, when yours will go, it's placed the message. When you see, for example, on WhatsApp, if you're trying to chat with someone and then your message was not sent first, what will happen is that your message will come last, yet you sent it at a certain time that was before the time of the other person responding. You see, I don't know. Anyone doesn't understand the example I'm giving? Is there anyone who's still confused? Anyone? Anyone? Anybody or anybody understand? Anybody understand what I said?
Yes, we understand.
Yes. So that's what WhatsApp will do, for example. Because imagine I'm sending you a message now. If my message is not gone yet, and then the next person writes the message and send back the message. So WhatsApp is receiving that message of the person before it will receive mine. So that is what we're talking about here. So watermark. So what does a watermark does? So every process that is happening, the watermark will create a timestamp for that data. Okay. So that will help you with processing time. Okay, so so this is the watermark principle. So it ensures that all data has been processed when the event's time-based window is destroyed. So this is the what the watermark will do. So a watermark is a increasing timestamp. So it's going to indicate at what time each event has happened. So without the watermark, what will happen to Flink is that we wouldn't know when to trigger window computations. You see, so for example, certain data has to happen. Let's say you have a certain window. So this data here, 21 and 19, was supposed to happen at 2 o'clock. But now it's not 2 o'clock anymore. It's 2:01. This data will not be considered because the window that you set for this data was 2 o'clock. So you're going to have a problem now with this data. So the reason why we put a watermark so that every data must first arrive, confirmed with the watermark, then processed to avoid issues. Okay. So these are just example of delay data that can come. We first allow a certain latency, so we allow for how long the data can be late in order for the system to still keep them in that window that was set. Okay, so how do we deal with delayed data? So in the event where we have a case of out of order, okay, a case of out of order. So we're going to deal with. There's a method to solve this. So what we're going to do is that in the system, we're going to reactivate the closed window and recalculate the correct result. So we're going to collect the delayed event and process them separately, or consider delay event as error messages and discard them. Okay, so by default, Flink will just discard this method where we consider the delay event as an error. But the solution to do that, we're just gonna collect all the events that come later and then process them, or else we're gonna lose certain data. Okay, so what will happen? So how the watermark will work is that each event will track the event's time progress. So we have, for example, we can set what's the current maximum event time, like the event time delay threshold that we can put. So maybe event can still delay for, I don't know, 5 seconds or something like that. So if after 5 seconds something is not done, what should the system do? And the system must restart again the process. Okay, so we create a time window for the operation. So when the watermark reaches the window operator, in terms of what window we gave the time. So let's say you say it's 12 o'clock. So something must happen from 12 o'clock to 12:02. So if the process is not triggered at that time, then we tell the system what to do, or maybe to collect the data and collect the event and process them later. Okay. So that's how we're going to deal with watermarks. So watermarks are going to be there to help us with identifying at what moment an event is happening and what's happening, and now can handle it if there's any delay. Okay, so basically, if let's say if we have late events, which means those events with timestamps which is less than the watermark, so we can still handle those events using what we call a side output. So the side output mechanism, so in the side output mechanism, so we take the delayed event and then we place it in an independent data stream. Okay, so this data stream can use a byproduct of window calculation result so that the users can obtain and perform special processing on the delay event. So this is one of the methods that can be used to deal with a delay event. Okay. So this is just a code to deal with the delay event. So after allowed latency set, delayed data can also trigger the window for outputs using the side output mechanism of things. We can obtain the delay data in the following way. So this is how we collect the delay data. Okay, so in terms of allowed latency, lateness, I mean, so in this case, when we know that we will specify what is the allowed lateness. So the allowed lateness will depend on the specification of the user himself. So you can say the operation needs to happen only for 5 seconds. So this is what happened when you, just for you to picture this, imagine when you're on a certain website, sometimes your network is bad, you're trying maybe to log in or to do something or to submit something on a certain form, and then it takes too long, and then next thing the system tell you time out, right? Because there's a delay, time out, so you have to restart the process. This is exactly what we're talking about. So the allowed lateness can be specified by the developer themselves and say after 10 seconds, if the user is still like the network is not well, or the user is still submitting, and then it needs to log you out, or it needs to cancel that submission. Okay. Okay, fault tolerance in Flink. So we have certain tolerance. So we have what we call a checkpoint. So how does Flink ensure exactly? Once it uses a feature called checkpoints to reset the system to correct state in the event of failure. So if there's an issue, there's an error or anything, Flink will be reset to the correct state by what we call a checkpoint. Okay, so basically all the states will depend on the checkpoint mechanism. So the checkpoint periodically creates distributed snapshots to back up the state of the program. So what is, if we want to really really understand what is a checkpoint, how can the checkpoint work? I'm trying to think what example I can give you. Okay, so to just understand, is that like the checkpoint in Flick, it's just a mechanism that will provide what we can call a fault tolerance. So it provides a fault tolerance by doing what? So on a certain time, like on a certain period, it's going to be saving the state of the streaming job. So as the files are being streamed, it's saving the state of the streaming job to see if there's an error or there's an issue, but it has a fault tolerance. So let's say, for example, out of a certain amount of data, if certain data are struggling or there's a delay for a certain amount of data, if it reached the fault tolerance, then it's going to stop the process. So if a failure occurs when the process is happening, so Flink will just restore the job from the last completed checkpoint, ensuring that we have at least once processing guarantee. So that's how it works. So Flinks will just generate checkpoint barriers at intervals on the input data and use these barriers to divide data during the interval into corresponding checkpoints. So when an application error occurs, the state of all operators can be restored from the previous snapshot to ensure data consistency. So think of checkpoint as a backup plan in the process. So those periodic snapshots that Flinks are taking, so basically this will be on the entire distributed pipeline. So from the source position to the state to the sync. So as the data come from the source, it goes to the operation, the transformation phase, to the sync, to the data sync. So at the regular intervals, Flink will consistently take those snapshots to store them, and then if there is an error, it's going to restore from the previous successful process. Okay, so it's kind of keeping it like it's saving the last change that was successful. Okay, so these barriers that are created from the input data, right? So these barriers will just be injected by a Flink into the data stream. Okay, so when an operator receives a barrier, for example, so it stops processing new records, right? So if it's processing the data and then there is a barrier, which is an error that happened, so it stops processing new records and then it has to deal with that operation first. Okay, so this will help to recover the system from failures and things like that. Okay, so when you think of these checkpoints, they can be triggered, let's say every 10 seconds. So every 10 seconds you check how the data work. So we can have a shorter interval, which is like 10 second or longer interval. But the shorter interval will help for faster recovery, okay, because it's quickly pick up the error and fix it. But the problem is we're gonna have very higher overloads because every time it has to do too much processes. But with a longer interval, the problem will be there will be less overload, but there will be a lot of reprocessing failures because we wait for a long time to find a problem. And then when we find the problem, when we put the barrier, we can have multiple problems in that set of data. So it's very important to define where and how the checkpoint state is stored. Okay. Okay, so checkpoint configuration. So by default, you need to note that the checkpointing is disabled. To enable checkpoint, we need to call the syntax enable checkpoint on the stream execution environment. So this is an example here where we creating those checkpoints. Okay. What we call here exactly once or at least once. So exactly once ensure end-to-end data consistency, which prevents the data loss and duplicates and delivers poor Flink performance. At least once applies to scenarios that have high requirements on latency and throughput, but low requirement on data consistency. So this is when we use checkpoint. So checkpoint will be required for stateful jobs. So jobs that require to identify and save the state of a certain operation. So we will need to set a checkpoint. Or when we have critical jobs that's critical for fault tolerance in production. So basically jobs or data that are very, very important. It's really critical. So we need to really make sure there is no error in the system. We need to make sure that there is no problem with how the data are moving. If you have to deal with a software that is using a robot for a surgery, you need to make sure there is checkpoints every 10 seconds, because if there's a mistake, you find out after a long time, then you end up, the consequences will be really, really unacceptable. All right. So this is why when you configure your checkpoint, it needs to be specified based on the requirement of the scenario. Okay, so in checkpoints, so we have a checkpoint timeout. We can specify a timeout period of checkpoint execution. So once this threshold is reached, Flink interrupt the checkpoint process and regard it as timeout. So this can be in your system. There is a time when Flink needs to check for errors, and while it's processing the check of errors, if he has done it for maybe 10 seconds, that's your timeout, it needs to stop. We stop that process and then we continue with the data. Okay, because if you don't place a timeout, what will happen is that Flink will continue placing barriers and stopping for errors, and that will freeze your system. So you need to interrupt it at a certain time. This is what we call a timeout. Okay. So we also need to set the minimum time between checkpoints. So if we time out now, after how long we're going to have a checkout point again. We need to check the number of concurrent checkpoints. Okay, so we can't have many checkpoints at the same time in the same data. And then we have externalized checkpoint. We can configure that. Okay. Okay, so this is an example of this is how we can use what we call save point and checkpoint. So when we trigger them, so the checkpoint can be automatically triggered and managed by Flink, but save points are manually triggered and managed by users. So the user decides when to save the information, but in terms of checkpoints, we can automatically set them in Flink. So the purpose of the checkpoint is to quickly restore tasks from failures. Okay, an example can be a timeout due to network issues, right? The purpose of save point is just to back up data as planned, for example, by modifying code or adjusting concurrency. Okay, so features for checkpoints, we have lightweight, automatic recovery from failures, and then the state is cleared by default after a job is paused. Okay, so these are the features of checkpoint. So when we have a checkpoint, if there's a checkpoint, the state will be cleared by default, and then we'll have an automatic recovery and then lightweight. But with save points, the features, it is persistent. We store data format, the format in which we'll store the data and allow code and configuration changes, and then we'll manually restore data from save points. Okay, so instead, in terms of storing the data, to store the data, we have a memory state backup. So this is an example of how it's going to happen. So we have the data will be, the state will be stored in what we call this task manager. So the task manager will save the state, but the checkpoint will be stored in job manager memory. So the capacity limit, so by default, we're going to have the size to 5 megabytes. So the maximum state size by default will be 10 megabytes. So the total size cannot exceed the memory of the job manager, because remember, the job manager needs to save the checkpoint information. Yeah. All right, guys. I think the rest tomorrow we're gonna start with the states backup to see a back end to see how we save the states. Okay. I think this will be all for today, but you need to know that in terms of the checkpoint and the save point, so the checkpoint are saved automatically. They are used for failure recovery. And then the checkpoint are deleted when the job stops, but the save points are set manually. And they are just used for plan upgrade, scaling, and you can store indefinitely. So you don't have to, you don't delete them, unlike the checkpoint. Okay. Yeah, so I think we're gonna carry on tomorrow. As for today, we can call it a day. Remember, next week we're starting with AI. That's gonna be more interesting because with AI we have more scenarios that we go through. Big data is more theory. That's why we can't have longer classes, because it becomes a bit tiring. Too much theory. All right, guys. Any questions before we can call it a day? Any questions?
Sir, can you please share these slides on the cloud that you have created? Because I just checked on the Huawei platform and these slides are not there. The videos, they don't cover these things.
Yeah, they are already on. This slide is already on the cloud. You must, when you log into the cloud, check the folder. What you call that? The folder data, big data. It's inside the folder build big data. So if you check in the WhatsApp group, in the description, you're gonna find the link to the cloud folder. Yes, you will find this slide. Did you get me?
Yes, thank you.
I will just, let me just check again. Let me maybe share that.
Oh, sorry for the late response. I was checking the photo. Okay, I saw that you have already uploaded the slides. Thank you.
Yes, yes, it is there. All right, guys. Any other question? Right. If there's no other question, we can just take the attendance and then we'll see you tomorrow.